Have you heard? Have you heard? The newest and best Bahamian resource for test preparation for BJCs and BGCSEs. Check us out on Facebook or at anansibahamas.com. Again, check us out on Facebook or at www.anansibahamas.com, where Mr. Ferguson is the COO. There are a lot of resources, especially for Bahamian students and Nancy Learning Technologies. Check us out. Good morning, students. It is so good to have you in lecture today. This is going to be lecture 6. Again, I'm so excited, so happy, so glad that you are in my class this semester. So just before we begin, I want to read this excerpt because I think it's very important. This is an excerpt from former President Obama's speech on the 50th anniversary of the March on Washington. And it begins, "But the good news is, just as was true in 1963, we now have a choice. We can continue down our current path in which the gears of this great democracy grind to a halt and our children accept a life of low expectations, where politics is a zero-sum game, where a few do very well while struggling families of every race fight over a shrinking economic pie. That's one path, or we can have the courage to change. The March on Washington teaches us that we are not trapped by the mistakes of history, that we are masters of our fate." So that's just a reminder, end quote. That's just a reminder that you must take agency. You must decide. You must make decisions to change. Be the change you want to see. Okay, so let's begin lecture for today. Okay. Just want to remind everyone, you are not alone. This is an academic community. Remember to get help when needed. Reach out to the university services if needed. Never give up. Keep trying. We are here to help you be ethical, intelligent, and successful scientists. However, at the end of the day, you must be responsible, ethical, and hardworking. So as we normally do, I'm going to give you some time, and I'm going to let you look at the structure, I want you to tell me the functional groups that you see, the functional groups that you see, the atoms that you see, as well as why do you think this polymer is so significant? Why do you think this molecule, why do you think these features of this molecule are so significant? So I'm going to give you some time to think about those things. Okay, so hopefully you saw that you have a phosphate group, you have an amine group. There are other functionalities that we can look into, but we're not going to discuss those now. We're going to look at the phosphate, you have the amine, you also have the hydroxyl. So just keep those in mind. And then you also have carbon, oxygen, phosphorus, nitrogen, carbon, all of those things. So those are the atoms that you see. Now, why is this important? This is DNA. DNA is a very important polymer in the body, biopolymer in the body. It plays a large role in cell replication. It plays a large role in the transfer of genetic information and expression of genes. And mutations in DNA have effects that are either immediate or downstream, and they are very significant. This is just another detailed view of the DNA, in which you have the different groups, but we're not getting into that, and we're not going to discuss in this class A, B, and C form. But we will note that DNA is very important, and those bonds that you see, those dotted lines, they represent hydrogen bonds. So a little bit about me. I am someone who values respect, integrity, and excellence, and I'm reminding you of the core values because it's important for you to know. I want you to work hard in my class because I want you to do well. Work hard, work smart. Okay, the goal of this class is to teach the chemistry content in an engaging manner that is relevant to the Bahamian student and digestible for their understanding. The sequence is as follows. Understand the fundamental concept A, practice problems relevant to understanding that concept, learn more nuanced details about that concept, and practice more complex problems that integrate the details and the fundamental understanding. So what we're going to talk about today is atomic spectroscopy and chemical bonding. We're going to look into line spectra and the Bohr model. We're going to look into electron configurations in the periodic table. In terms of drawing those orbital diagrams, I'll teach you a little bit about that, but we won't spend a lot of time on that. We won't spend any time on that in this lecture, but we'll talk about it next lecture. So I want you to be able to use the periodic table to write abbreviated electron configurations and determine the number of unpaired electrons in an atom. I also want you to be able to understand chemical bonding. So let's look at this periodic table. What do you see? Why is it unique? And what stands out to you? Okay. So if you look at the periodic table, you have different blocks or different regions of it labeled with different letters and also different numbers. We know from our previous discussions that these designations, so the letter designations come from, they designate are based in the angular momentum value. So when L equals 0, we get S. When L equals 1, we get P. When L equals 2, we get D. And when L equals 3, we get F. And then we also know that these values, these numbers in front of them, these integer values are referring to the principal quantum number, or the N value. So that's that. So this is the S block. This is how these things are typically described. This is the S block. This is the P block. And remember, as you look at this, you can see everything has an S. This is the P block. This is the D block. This is the F block. So the alkali metals, alkaline earth metals, groups 3 to group 8, transition metals, and then your lanthanide actinide series. Just keep that in mind. So let's be specific. If you look specifically at hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine and argon, potassium, and calcium, the thing that stands out, or the thing that's important for you to know, is that if you look at the electron configurations, you can write the electron configurations of basically every element in the periodic table with this understanding. There are some nuances for some of the transition metals, but we're not going to get into that during this lecture. But we're going to look at the first 20, and if you look at it, so if I look at hydrogen, it's in the S block in the first period. So the period gives us, for that understanding, we know that hydrogen is going to be 1s, and it has 1 electron. We know that's its atomic number because we're assuming we're writing ground state electron configurations, and so hydrogen is going to be 1s1. And then that same understanding, we're just reading off the periodic table based off the designations that we see. Helium is going to be 1s2 because it has 2 electrons. Lithium has 3 electrons, so it'll be 1s2, 2s1. Beryllium is 1s2, 2s2. Boron is 1s2, 2s2, 2p1. Let me just show you boron, 1s2, 2s2, 2p1. This would be 1s2, 2s2, 2p2, 1s2, 2s2, 2p3, 1s2, 2s2, 2p4, 1s2, 2s2, 2p5, 1s2, 2s2, 2p6. So let's go here. And the abbreviations, or the abbreviated format in which you can write the noble gas and in brackets, and then you can continue writing the electron configuration. So I could say neon 3s1, neon 3s2, neon, because basically it's saying because the thing continues, the electron configuration continues. So instead of writing 1s2, 2s2, 2p6, 3s1, I could say neon 3s1, neon 3s2, neon 3s2, 3p1, and so on. And I'll just continue. Neon 3s2, 3p3 is phosphorus. Neon 3s2, 3p4, sulfur. Neon 3s2, 3p5 is chlorine. And then argon. You can write that. We could say neon 3s2, 3p6, or we could say argon. Then typically you write that neon 3s2, 3p6, and then we'll write potassium as argon 4s1, and calcium is argon 4s2. So as you can see, if you follow along and you just be detailed and meticulous, you can see how the electron configurations, you can write them from the periodic table. So let's draw it back. Let's go back. Because we're going to go back so we can launch further forward. So de Broglie's work is applicable to all matter. All matter of mass m with velocity v would give rise to characteristic wave-like and particle-like properties. Hence we have the wave-particle duality. So lambda is h over mv. De Broglie published his theory, and within a few years, the wave properties of the electron were demonstrated experimentally. So let's keep it going. Atomic spectroscopy. Atomic spectroscopy, as we discussed in last lecture, it gives us an idea of how the wavelength and emission spectra of each atom correspond to the electron transitions between the quantum mechanical orbitals. So if we look at this equation, we can see that change in energy is equal to E final minus E initial. And then we also look at Rydberg's equation, or a version of Rydberg's equation, in which we have Rydberg's constant, and of course those values should be squared. For the quantized states, NF and NI, this should be squared. So let's keep it going. How do you create a spectrum? How do you create a spectrum? Well, you create a spectrum. A spectrum is produced when radiation from such sources is separated into its different wavelength components. So what does that say? Through the use of a light source, a slit, and a prism, you are able to disperse or result in dispersion of light. You see a continuous spectrum in this instance, and then you also see a discrete spectrum or a spectrum in which you have discrete wavelengths, specific wavelengths. That's going to be a line spectrum as opposed to a continuous spectrum. So it has specific wavelengths. Just keep in mind, for continuous spectrum, an example of a continuous spectrum would be a rainbow. So an example of a line spectrum would be what we see right here. And then a line spectrum contains radiation of only specific wavelengths. And these spectra are obtained from electrical discharge from sodium or hydrogen or some other element. So what is the Bohr model? Let's be going backwards so we can launch forwards. What is the Bohr model? The Bohr model was based on three postulates. Only orbits of certain radii corresponding to certain definite energies are permitted for the electron in a hydrogen atom. 2. An electron in a permitted orbit has a specific energy and is an allowed energy state. An electron in an allowed energy state will not radiate energy and therefore not spiral into the nucleus. So just keep that in mind. It's kind of a classical paradigm though. And then energy is emitted or absorbed by an electron only as the electron changes from one allowed energy state to another. This energy is emitted or absorbed as a photon. E equals h nu. So as we said earlier, if you process these ideas, or if you want to think of these ideas in a sequence, in terms of how the people or scientists came up with them or worked towards them, you can think of Max Planck starting the race, Albert Einstein taking the baton, and then passing it on to Niels Bohr, and then passing it on to Werner Heisenberg, or news while passing on to Schrodinger. So that's kind of a way to think about this concept through the analogy of a relay. So this is a good point in this video to pause it and also to practice questions on Rydberg's equation. I will assess your understanding of Rydberg's equation. It's very important. It's good to understand. It ties well with the Bohr's model. So I want you to understand this equation. So please practice it. I will release a practice problem video, another one, problem solving session video that covers a wide range of problems. And if you practice that problem, if you practice the homework, the quizzes, as well as work through the videos, you should be in good shape for the exam. Okay, remember my goal is not to overwhelm anyone or frustrate anyone, but my goal is to help you learn the material well. So at the end of the day, you are responsible to be hardworking, ethical, and responsible. Okay, so the limitations of the Bohr model. The Bohr model has limitations. It only explains the line spectrum of the hydrogen atom well, and it avoids the problem of a negatively charged electron falling into the nucleus. So chemical bonding. What is bonding? Why is it important? What are the types? And what types of elements tend to participate in the different types of bonding? So bonding is a theoretical construct that involves the attraction of the electrons of an atom to the nucleus of another atom. So it's basically saying that bonding is a way we understand how elements come together, how atoms come together, how they combine together. Bonding gives us a good foundation to understand chemical reactivity. Bonding is very important. Bonding typically occurs and it provides it helps for atoms to become stable. Atoms become stable. Why is it important? It occurs as a means for elements to share, attract, or distribute electrons in order to become stable. Bonding is important because it provides a foundation for chemical reactivity. The types of bonding are covalent bonding, ionic bonding, additive bonding, additive bonding. Covalent bonding occurs when atoms share electrons as a means of bonding. So what does that mean? You have your non-melds and your non-melds, and they're sharing electrons. So think about this. Ionic is almost, and this is an analogy. An ionic is almost like you donate an electron, or you have ions coming together. Donate an electron. Covalent bonds, you have sharing of electrons. Additive bonds, you have one atom contributing to the bonding pair. So ionic bonding occurs between metals and non-metals. A classic example of this is with sodium chloride, magnesium chloride, potassium chloride, and what do you see there? You have your metal and you have your non-metal or your halogen coming together to form an ionic compound. This is bonding between ions. This occurs between cations and anions, and the Born-Haber process allows for us to understand this well and see it unfold. Okay. So additive bonding or covalent bonding. This is bonding that occurs as a result of one element donating the entire bonding pair of electrons to form a coordinate covalent bond, coordinate covalent compound. This type typically occurs between elements and molecules or metals and ligands. So let's delve deeper into the material for today. So what are we going to discuss? We're going to discuss Lewis structures. We're going to discuss the octet rule. We're going to discuss briefly electron shell filling. So from 2, 8, 8, 18, 18, 32, and 32. We're going to discuss some exceptions to the octet rule, which typically occur with your incomplete octets with boron and beryllium, and then also with your expanded octets from third period beyond. We're going to discuss ionic bonds. We're going to discuss electron configurations of single element ions. We're also going to discuss polyatomic ions, the nomenclature and formal charge. We're also going to discuss resonance structures, how to determine formal charge, covalent bonds, multiple bonds, bond polarity, dipole moments, bond length, bond strength, and bond enthalpy. Like I said, this will be a weighty lecture, so I need you to pause it as much as possible and take notes. So, bonding models. What is a bonding model? Remember, I told you a bond is a theoretical construct. So, our understanding when we first started off, our understanding of these things was progressive. In some ways, we're still understanding these things better and better and better. But first off, the Lewis model. It's a model that helps us understand and make educated predictions about chemical observations. Now, B, the valence bond theory. It provides a more quantum mechanical treatment of the electron, but it doesn't really address the delocalization of the electrons around the entire molecule. And then you have the molecular orbital theory. So it provides a full quantum mechanical treatment of the molecule and its electrons as a whole. So you have your Lewis model, you have your valence bond theory, and you have your molecular orbital theory. And I'll just throw this in there. The sequence in which you typically learn these concepts are the Lewis model and valence bond theory, and then you also introduce to hybridization, in which you look at the mathematical mixing of orbitals, and then you proceed to molecular orbital theory. That's typically the sequence that is run through. But today we're focusing on the Lewis model. The Lewis model. It is named after Gilbert N. Lewis, and in the Lewis electron dot structures, the valence electrons are represented as dots with a chemical symbol to depict molecules. Now, how do I draw a Lewis structure? The first thing you do is you note the total amount of valence electrons in the molecule. Then you place single bonds between each atom. Then you subtract 2 electrons based on the number of bonds added. Then you ensure each atom has an octet. Exceptions are with atoms with expanded octets, with third period and beyond. For example, the sulfur and arsenic. And then we'll discuss this later, but the seal of the deal, if you want to come up with a term, or the icing on the cake, is when you write those structures that minimize charges. That's when you incorporate the idea of formal charges into this. So types of bonds. Bonding theories help us predict the circumstances under which bonds form and also the properties of resultant molecules. So as I said earlier, ionic bonds occur between metals and nonmetals, involves the transfer of electrons. Covalent bonds occur between nonmetals and nonmetals, and involves electrons being shared. Metallic bonds involve your sea of electrons. You have electrons being pooled, and that occurs with metals. So, during this segment of the class, as I mentioned earlier, we'll discuss writing electron configurations. The first thing to do, determine the total number of valence electrons, and you get this from your group number. 2. Using the periodic table as a guide with the S block, P block, D block, and F block, which I spoke about earlier in the video, write out the electron configuration. It should read configuration, sorry about that. And then we will typically go as far as up to 4s2. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 for calcium. However, I just wrote out a longer version or longer electron configuration for your education purposes. Now, this is very important. Very, very important. When you are breaking a bond, it requires the input of energy. Anything that requires the input of energy typically is going to be an endothermic process. It requires energy input. And if you think about it from the stance of a reaction coordinate diagram, you typically result in a product that has a higher potential energy. Now bond forming is exothermic because energy is released, and typically results in a product that has a lower potential energy if you look at the reaction coordinate diagram. So just keep that in mind. Think about that, pause the video, think about that, and say, why does this make sense? Or how can this make sense to me? Okay, Born-Haber cycle. Now typically in the Born-Haber cycle, which is a process that we note when we are looking at how a crystalline of an ionic compound forms, you have your metal going from solid to gaseous, and then the halogen Going from atoms to molecules, the metal is then ionized, gaseous halogen or non-metal is ionized as well, and then it's combined to form the crystalline lattice. So, lattice energies become less exothermic with increasing ionic radius. And we can go deep into that, but I just want you to look at that for face value for now. Because we can talk about polarizability and all those other things and how electron clouds are affected, but we're going to talk about that now. Lattice energies become more exothermic, more negative, with increasing magnitude of ionic charge. A lot of these ideas are based or have a pillar in Coulomb's law. Okay, so ionic compounds in medicine. Ionic compounds are used in medicine to strengthen teeth and even as antiseptic and disinfectant. So covalent bonds. Covalent bonds involve the sharing of electrons. The shared pair of electrons is called a bonding pair, while a pair associated with only one atom is called a lone pair. Covalent bonds occur with nonmetals and nonmetals. Now let's talk about some exceptions to the octet rule. The octet rule is like the big chief. Salute to the octet rule. However, there are exceptions. Not every situation obeys the octet rule. There are atoms that have energetically accessible d orbitals and can accommodate extra electrons, for example, sulfur and phosphorus. That kind of gives us an understanding as to why they have those particular geometries, whether it be octahedral sometimes for sulfur, or trigonal bipyramidal sometimes for phosphorus, so phosphorus pentachloride, for example. Then you also have your expanded octets tend not to occur in second period elements. But also, you need to remember that boron and beryllium have incomplete octets, typically seen. Okay, so let's keep going. Polyatomic compounds. Let's talk about some nomenclature of ionic compounds. Okay, binary compounds contain only two different elements. The names of binary ionic compounds are written as such. You have your name of your cation, the base name of your anion, then the ide. So for example, sodium, chloride, magnesium, chloride, magnesium, bromide. So just picture that. Ionic compounds with varying valency, so for example, ferrous and ferric, stannous and stannic, plumbous and plumbic. All of those things, it points to or it shows us that those metal atoms, metal ions have different valencies, resulting in different metal cations, different charges. And for example, iron, if you're writing a compound with a iron 1, for example, you would say iron, and in brackets we have the charge, so we'll have 1, and then the base name of that anion, chlor, and then ide, so iron 1 chloride, iron 1, or iron 2 chloride. Okay, so names of molecular compounds. The prefix, and then the name of the base element, and prefix, and the name of the second element plus ide. So, for example, dinitrogen monoxide. So just keep those things in mind. Remember, a molecule is referring to something with more than one atom. The compound is something that has two different atoms. So a molecular compound is basically referring to a substance that's made up of more than one atoms, and those atoms are different. Okay, let's talk about some polyatomic ions. This is adapted from Navaldo's Tro's book. So this picture rather is adapted from Navaldo's Tro's book. And what we want to note here is you have your nitrate, NO3 minus, your sulfite, NO3, 2 minus, your sulfate, SO4, 2 minus. And what we want to know here is they are polyatomic, more than one atom, and they are also ions. They have charges. So let's keep going. Resonance structures. Why should I care about resonance structures? Why should we care? Resonance structures are structures that provide a description of how the electrons are situated around a molecule. It's almost if we had say a molecule was walking across the road, and we took pictures of it as it walked across the road. So we were accounting for how the electrons were positioned at each point across the road. Now, the thing to remember is, because electrons are moving all around and they're distributed in an electron cloud, noting them, and this is based in or really tied well to the Heisenberg uncertainty principle. We cannot give a complete description just with one resonance structure of the electron distribution in a molecule. You can't note that just because electrons are not just static, they're not just stuck. And that's the reason why a resonance hybrid gives us a good understanding of the real description or real notation of the electrons in an atom. It's one of the best qualitative descriptors of the positions of electrons in a molecule. And also, when you're drawing resonance structures, it's important to note the formal charges. So how do you solve a formal charge? Valence electrons, you took up the valence electrons, which you get from your period number, from your group number, excuse me. The valence electrons minus 0.5 bonding electrons minus your non-bonding electrons equals formal charge. So one more time, draw it back. Valence electrons, which you get from your group number, minus 0.5 bonding electrons minus non-bonding electrons. So another way to put this, when you write your Lewis structure, you take your valence electrons minus your bonding electrons minus your non-bonding electrons. So 0.5 bonding electrons, that's going to be your sticks in your Lewis structure. Non-bonding electrons will be your dots. So valence electrons, which you get from your period number, from your group number, and then bonding electrons will be your sticks, non-bonding electrons will be your dots. Best resonance structure follows the octet rule and minimizes formal charge. Let's keep going. Electronegativity. Electronegativity is essentially the ability of an atom to attract electrons to itself. A bond's polarity is determined by the electronegativity difference between two different elements. The greater the electronegativity difference between the atoms, the greater the difference in polarity. And how do we get these electronegativity values? We look at the Linus-Pauling scale, and you can look that up. So percent ionic character basically is your measured dipole moment of the bond over dipole moment if the electron were completely transferred times 100/1. So bond length and bond enthalpy. A bond's length is dependent on the type of bond. The greater the bond order, the shorter the stronger the bond. So for example, a single bond is longer than a double bond, which is longer than a triple bond, and a triple bond is stronger than a double bond, which is stronger than a single bond. It's just giving you an idea of electron density in terms of electron density, electron distribution, and how those things are attracted, the strength of the attraction. That's basically what it's describing. Also, bond enthalpy is associated with bond energy. Bond energy is the energy required to break 1 mole of the bond in the gas phase. Bond enthalpy is the heat energy released or absorbed when bonds form or bonds break, respectively. So we're going to go back and we're going to review the concepts. We've discussed the content for today, and we're going to go back and review these key principles. The Heisenberg uncertainty principle. And what does it say? Heisenberg uncertainty principle basically says that the more we know about the position of an electron, the less we know about its momentum at that instant. Pauli's exclusion principle. No two electrons can have the same 4 quantum numbers. Those 4 quantum numbers are N, your principal quantum number, L, your azimuthal or angular quantum number, angular momentum quantum number. Then you have your M sub L, which is your magnetic quantum number. And then you have your M sub S, which is your spin quantum number. None of those four values can be the same for an electron. Talk about the ground state. All these rules are typically referring to electron configurations to the ground state. And then Hund's rule. What is Hund's rule? When filling the general orbitals, electrons fill them singly first with parallel spins. And then Aufbau's principle, which comes from the German Aufbauen, which basically describes how we write electron configurations, how we build up from S to P to D to F. and the wave particle duality, which comes from de Broglie's ideas, in which we understand, which stems from de Broglie's ideas, which we understand that matter has both wave-like and particle-like properties. So remember those four quantum numbers, they are solutions to Schrodinger's equation. And if you want to read more about these things, we can discuss, or we have discussed those in previous lectures. So just remember, these principal quantum numbers are these four quantum numbers are very important for this class, and you will be assessed on these. Your understanding will be assessed. So once again, I hope everyone is doing well. I hope everyone is enjoying the class and working really hard. So take care and see you in lecture next week.